Hi everyone! Today we're going to continue our introduction to waves by first reviewing some of the important material from last week's lecture, surface gravity waves mostly, and then shifting our discussion to internal waves. So first we might remember from last week's lecture that waves travel through a medium, and it requires a displacement force and a restoring force. For this course, we classify displacement forces as either internal or surface. A restoring force is dependent on the medium waves are traveling through and also the type of wave. Some common waves found in the ocean are listed out with their disturbing forces, either I or S, internal or surface, along with their restoring force. So sound waves are longitudinal waves. They're disturbed internally and they are restored by compressibility. Capillary waves are very small ripples observed at the water's surface, usually a result of the wind, or can also be seen by tossing a rock into a still pond. The restoring force of capillary waves is surface tension. Surface gravity and rotational gravity waves are both disturbed on the surface, and both are restored by gravity. Rotational gravity waves are restored by both gravity and the Coriolis effect. Internal waves, which we'll be talking about today, are obviously disturbed internally, and they are restored by gravity. Rotational internal waves are also internal, and they're also restored by gravity, but they're restored by both gravity and the Coriolis. And finally, Rossby waves are internal waves, and they are restored by the beta effect, which again is the change in the Coriolis force with latitude. Okay, so once again, we have our simple wave or our plane wave, which these are long crested waves with a sinusoidal surface shape. The distance from the mean state of rest is amplitude A. The distance from crest to crest or trough to trough is the wavelength lambda. T is the wave period. K is equal to 2 pi over wavelength lambda, and this is what we call the wave number. And similarly, sigma is equal to 2 pi over the wave period t, and this is what we call the angular frequency. The instantaneous displacement of the wave is eta, and equal to a cosine of kx minus sigma t. This is known as the phase of the wave, which again is like the position of the wave within a cycle. The phase and group speeds are important properties of waves. The phase speed, or Cp, is sigma over k, or the angular frequency over the wave number, which is equal to the wavelength over the wave period, and this is measured in meters per second. The phase speed describes how fast an individual wave travels through a medium. The group speed, on the other hand, describes how fast a packet of waves travel through a medium. Group speed, Cg, is equal to the change in angular frequency with respect to the wave number. A packet or group of waves will often have many waves all traveling with different wavelengths and at different speeds. This causes wave dispersion, which can be described by the dispersion relation, the relationship between angular frequency and wave number. Okay, so the first type of wave we talked about were surface gravity waves. These waves are restored by gravity, and the equations we use to describe them are a balance between the Eulerian rate of change and the pressure gradient, and of course gravity in the z direction. We went through in the last lecture and linearized the equation and found that these are only good if the amplitude is much less than the wavelength. The dispersion relation for surface gravity waves is sigma squared is equal to gk times the hyperbolic tangent of kh. I don't think we talked about this in the last lecture, but the hyperbolic tangent can also be written as e to the kh minus e to the negative kh over e to the kh plus e to the negative kh. The dispersion relation can be simplified. In shallow water, kh is much less than 1, since the depth is much less than the wavelength. And using the small angle approximation, the hyperbolic tangent can be approximated to simply kh. It follows that our dispersion relation can be simplified to k square root of gh, which allows us to solve for group and phase speed. We find that both Cp and Cg are equal to the square root of gh, meaning that the shallow water surface gravity waves are non-dispersive. Because we have this factor of h in both our phase and group speeds, we note that both velocities decrease with decreasing water depth h. This results in wave refraction, which happens when a wave approaches a shoreline at an angle. The part of the wave crest closer to the shore is in shallower water, and thus moving slower than the part of the wave away from shore in deeper water. This refracts or bends the wave as they move to shallower waters. It also focuses the wave energy on the region of shallower waters, creating larger waves and great point breaks for surfing. Deepwater surface gravity waves are surface waves that form where the water depth is much larger than the wavelength. In this case, kh is much larger than 1. Again, we can write our hyperbolic tangent function here, but we now note that with a large kh value, e to the negative kh goes to 0. We are left with e to the kh over e to the kh, which is simply equal to 1. We can therefore simplify our dispersion relation in deep waters, to the square root of gk, and use to solve for the phase and group speed. In this case, we found that the phase speed is equal to the square root of g over k, and the group speed is half the phase speed. Therefore, deep water surface gravity waves are dispersive, and long waves travel faster than short waves. In this case, neither phase nor group speed depend on water depth, so deep water waves can propagate through regions of varying water depth without changing speed. We'll now switch gears and talk about internal waves, and this will set us up for the internal wave demo by Group 6 in class on Thursday. Alright, so as we've discussed, the restoring force for internal waves is gravity. In the ocean, internal waves require two layers with slightly different densities, and can therefore travel at the interface between the layers rather than at the sea surface, where the density difference is much greater. Because of this, internal waves are much slower than surface gravity waves. Deepwater internal waves, or short waves, are those in which h1 and h2 are much larger than the wavelength. hence the name short waves. In this case, the phase speed is equal to the square root of g over k times the change in density between the two layers over rho 1 plus rho 2. We note that the change in density over the density is going to be much less than 1, and again, we see that the phase speed of internal waves is going to be very slow. The group speed is again half the phase speed. Just for the sake of it, note that if rho 1 is equal to 0, or the upper layer is air, and this wave is happening at the surface rather than internally, delta rho is equal to rho, and that term becomes 1, so that the phase speed is equal to the square root of g over k, which is a deep water surface wave. A shallow water internal wave, which typically happens in the thermocline in the open ocean, is one such that h1 is much less than the wavelength, but h2 is greater than the wavelength. We see why this happens. This is confined to the thermocline surface layers, where density changes rapidly close to the surface. In this case, our phase speed is equal to the square root of g prime h1, where g prime is equal to the gravitational acceleration g times delta rho over rho. And finally, we have shallow water internal waves, or waves such that h1 and h2 are both much less than the wavelength. In this case, our phase speed is equal to the square root of g prime times h1, h2 over h1 plus h2. We've mentioned a few times that internal waves propagate at slower speeds than surface waves. It may be helpful to compare shallow water internal waves to shallow water surface waves to get an idea of the difference in speed. Let's say h1, the height of the top layer, is 100 meters, and the density of this layer is 1,024 kilograms over meters cubed. In the bottom layer, the height is 200 meters, and the density is 1026 kilograms per meters cubed. Now we can ask, how fast would a surface wave propagate? Plugging in values for phase speed, we get the square root of 9.8 times 300. We use the total depth here since the surface wave is traveling over the surface rather than on the interface between the two layers. When solving for phase speed, we arrive at 54 meters per second. Now, when we solve for the phase velocity for an internal gravity wave, we find that the propagation speed is much slower. In the case of continuous stratification, density change with depth is constant, and therefore n squared is constant. We now find that internal waves have both horizontal and vertical components of propagation, and our equation for instantaneous displacement will now also have horizontal and vertical components. The dispersion relationship for internal waves is written as below. Now, if the frequency is small enough, or in other words, the wave period long enough, we need to consider the effects of rotation. The balance becomes between pressure gradient, Coriolis, and acceleration, and we need to include the Coriolis force in our dispersion relationship. Alright, that's all I have for you guys this week. There is some additional reading from the Knaus book, so check that out. And also this week, our form is going to be the group background material you began in class on Thursday. One person will need to post your motivation and background that your group worked on together, and you will each need to comment on 2 proposals that are not your own. There are more details in the description of the forum. Thanks guys, see you in class on Thursday.